Super. Okay, we can start. Wang, okay? Okay, we can start. Wang, okay?
Can you see my screen?
Not yet.
Not yet. Okay.
Give me 1 second. Okay, good morning, good afternoon, good evening, everyone. I'm Professor Marco Rivera from the University of Talca. Welcome to the session number 8 of the online meetings of the Worldwide Energy Network. And today we will have the presentation of Professor Wang, who is working in the Center of Reliable Power Electronics and the vice leader for the Efficient and Reliable Power Electronics Research Program at Aalborg University in Denmark. His research regarding challenges in modeling and validation of power electronics component failure mechanisms and application issues in system-level predictability, condition monitoring, circuit architecture, and robustness design. Professor Wang, welcome to our session.
Thank you, Marco. So shall we start now?
Yes, we can start.
Yeah, I can share my screen just a moment. Can you see my screen, Marco?
Yes, we can see.
Great. Okay, hello, everyone, and good day. Since we have people from different countries, welcome to this presentation. It's my great pleasure to give a presentation on this worldwide energy network. Since Marco told me that this presentation will be about up to half an hour, so I will go a little bit quick in the slides, and then for the rest of the time, if we have any questions, so we can discuss, maybe go back or forth to some of the slides materials. Aalborg University is in the north part of Denmark. It was a relatively young university that was established in 1974, in case some of you are not familiar with it. And the Aalborg University, we implement a very special education model we call problem-based learning. So our students work teams. They get their ECTs, their credits, 50% from the project work every semester from year 1 to the master, if you go for the master study. And we come from the energy technology department. So this energy technology department is actually equivalent to Department of Electrical and Electronic Engineering in many of other universities in the world. And also, in addition to that, is work on the thermal, fluid power, and so on. So this is areas where relevant to our department's research activities, like we work on energy storage, renewable energies, and power systems. And then when we look at this photo, we see there are a lot of power electronics that link those between the energy generation and the utilization of the electricities. Here is a research program in our department. Basically, we organize the research activities in the department based on different research programs. we have a core research program related to power electronics that is efficient and reliable power electronics. And then we have a number of programs that is application oriented, like the wind power, the PV, and e-mobility, microgrids, and also several other research programs that where power electronics are used, maybe not as often as these four research programs for that. It's a relatively big team here. About 60% of the manpower in the department work on the power electronics related research activities. Here is talking about the education model. As I mentioned, usually the students work from year 1, 4 to 6 students as a group. They continue this teamwork year by year so that they work 50% from the semester projects. For the PhD program, we held a number of, we call industry PhD courses. So those courses are open to companies also, or other students from other universities for that. Here are just a number of courses listed here, like reliability of power electronic systems. That is quite relevant to what I talked here now. And then we have some course on the packaging, capacitors, DFMEA. This is also quite related to the reliability of power electronics. So in this presentation, it mainly consists of 3 parts. The first is about why we talk about the reliability of power electronics. And then the second part, we'll talk about some scientific challenge on reliability of power electronics. And third part, a number of research activity examples will be introduced. So let's look at power electronics. I think we're familiar with that. Power electronics is kind of interface between the electricity generation and consumption. And this could be bidirectional. There are different kinds of topologies or control methods that can be utilized nowadays to implement a power converter. But if we look at the component level, there are several kinds of components. The majority of the converters consist of those components like switching device, capacitors, magnetics, and some resistors, and heat sinks, fans, maybe the cooling system, and so on. And then we use controller to do that. And here's a chart that try to show the different stage of the power electronics. First of all, it's heavily impacted by the development of power semiconductor device, because this is the key components in the power converters that can be controlled. This is the only component that can be controlled on and off in the power converters. And then if we look at power electronics itself, we see that between 1950s to early 2000s, we call here is phase 2. It's about a lot of research search for circuit topologies, control, and modeling methods, and try to increase the switching frequency and try to improve driving technologies, and digital control is gradually used in power electronics. So those topics nowadays are still very important. There's still a lot of challenge for that. But in the last 2 decades, we do see that there are more and more application-driven research in power electronics. That is people talk about renewable energy application, automotive, aircraft, and so on. So those research activities are dedicated to address the specific challenges in those applications. We talk about packaging, thermal management, EMI, EMC, reliability, and large scale of power electronics converter systems used in power systems. And many are digitalized, controlled for that nowadays. So we could see that if we look at the phase 3, the industry start to pay more and more attention on the reliability aspect, performance of power electronics. And yeah, I will skip this. There are different motivations to look at reliability of power electronics. The first one is that the increasing use of power electronics. If we look at the utilization end, there is electrification of transportation. More and more power electronics are used, but also power electronics are used to replace some of the existing systems, long power electronics based systems. For example, when we talk about the solid state transformer, So this is a very typical structure of the traction motor system. So we have 15 kilovolts or 25 kilovolts AC to supply this traction motor. So usually there is a line frequency. So this line frequency in some countries means 16.7 hertz. In some countries means 50 hertz. So in this way, especially when the frequency is 16.7 hertz, the size of this transformer is really large. And then there's a chance for us to use power electronics-based converters to replace this line frequency transformer. So ABB has demoed one of these technologies, like here. This is where power electronics are used to replace some long power electronics systems in the past for that. If we look at from the energy generation side, we all know that renewable energy becomes more and more penetrated in our modern electricity system. So we see this example for the full-scale power converter for the wind turbine system. So in these applications, the reliability and security of supply is very important, and also the cost of energy is very important. The cost of energy is relevant to the maintenance operation cost and also the energy generation, the annual energy generation. So in that way, the reliability is important part for that. You may argue that, okay, even though the power electronics is increasing use in our system, but what about if it is itself is very reliable? So we don't need to pay too much attention to that. But the reality shows that power electronics are actually usually one of the reliability critical part in the big system. Usually they're used in big system. Here I give two examples. The first one is related to a PV application. This is a survey done by St. Edison. So basically they collect the surface tickets. A surface ticket is related to a record of an issue affecting the PV system. So the PV system locates in US, in Europe and Asia. So mainly dominantly in US, the data come from there. But there are two conclusions. The first one is in these collected 3,600 surface tickets, about 43% are related to PV inverter. And then because of this 43% of the failure related issues, it causes 36% energy loss. So if you look at the energy loss, this is mainly due to the interruption of the energy generation. That means even there is a very sunny day, but because of the fault in the inverter system, so there will be no energy generated from the PV panel. And the second conclusion is 50% of the energy loss actually caused just by 5% of the instance. So this gives us opportunity that, okay, maybe we don't need to look at all of the failures because of the limited resource. And if we can deal with this 5% of instance, and then we can cut the energy loss by half. So another example, this relatively old survey comes from a team from UK, this Rely Wind project. So in this report, it collected data from 350 onshore wind turbine in very length of time. So in total, there are 35,000 downtime events. Among that, the power converter contribute to 13% of the failure. And because of the 13%, it caused 18.4% of the downtime. The downtime is also caused this, the interruption of the energy generation for that. So these two examples are the specific examples, but relatively they represent a large database in the public domain. Even though for a specific project, maybe the conclusion could be different, but these represent a typical conclusions for that regarding the reliability of power electronics. And then at this Center of Reliable Power Electronics, we have worked very closely with industry. So from their perspective, we see there is reliability challenge in the future that in the future we would like to have the customer, the user, the owner of the system really would like to have peace of mind. That means if we say this system could run for 20 years, and then they would like just run the system for 20 years without any worries or concerns. And so in this way, we need this we call predictive maintenance. So instead of when the system fails, we do replacement, or we do the regular maintenance, like every 6 months to do a check, or every 5 years to replace the capacitor bank and so on. In the future, if we want to really optimize the maintenance, we would like to have to estimate the healthy status beforehand, before the assembly or system fail, and then to do the maintenance based on the conditions, based on the healthy conditions. And in terms of R&D approach, this design for reliability becomes important. This is a design methodology for power electronics converters and also for many other applications. And R&D tools, in order to do this, the fundamental thing is that we need to understand the failure mechanisms. We need to understand why the components or interconnections fail, what kind of failure could happen. And also, beside that, we need to understand the feed, the load, because we need to understand the environmental and operation conditions for that. There is a trend from industry, besides selling the product, selling the service is becoming a trend for that, so that they can provide the service. Like in the wind industry, now we see more and more like 20 years, 25 years, even 30 years of service contract for that. And with the development of IoT or digitalization, we see a lot of data will be collected from existing power electronics products or the next generation of power electronics products. So this data combined with the understanding of the failure mechanisms, it will provide new opportunity for us to utilize those information to do reliability aspect research. Here are typical lifetime targets. The conclusion here is that we could see from different applications, the requirement is really, it varies a lot. So when we design the power converters, we need to take into account the specific lifetime targets. Another thing in the past years, we see there is a change in minds in reliability culture. For example, in the traditional design, like the power electronics designers and reliability engineers, somehow they worked in a relatively separate way. The power electronic designers design the products and then do the laboratory testing, and then they pass it to the reliability engineer to do the further like qualification testing and so on. If that does not work, they will go back to the design team to revise the test. But now we see companies, at least some of the companies, that try to have an integrated reliability program in the power electronics product design, that they try to consider the reliability as a performance factor as early as possible in the product development phase, like in the concept and design phase. So how that will have impact for us to choose the topology, to choose the right components in order to fulfill the reliability target. Because otherwise, if there is any design defect happens in the concept and design phase and have not been detected before it goes to the customer hands, and this may cause huge economic loss. I think here's one example is in this Ganex Load 7 in 2016. Maybe we still remember that this caused a lot of trouble for Samsung. And in the end, 96% of the 3 million Load 7 has been returned globally. And this caused estimated $5 billion US dollars economic loss for that. But the issue is coming from the battery. The battery short circuit that caused this fire in that fall of 2016. Okay, scientific challenge. We have talked about reliability, but maybe not all of us are familiar with the exact definition of that. So basically, in reliability engineering, when we talk about reliability, that is a probability. So a probability is a number between 0 and 1. Okay, a probability that item that can fulfill the required function. So there is a predefined function that the item need to fulfill. If it cannot fulfill this required function, it's considered as a fail case. And then under given condition, given time intervals. This is very straightforward, but another term is not so straightforward. Actually, when we talk about the lifetime, we say this product has a lifetime of 5 years. But what does this 5 years mean? Does it mean that within these 5 years, there's no single failure, or does it mean at the end of the 5 years, all of the items will fail? So this usually make us some confusions when we see reports or when we discuss with people, and then we see that there are some confusions of that. Actually, lifetime there are two lifetimes. The first one is about lifetime for individual item. So in this way, we see it is a time when this item fail, cannot fulfill this required function anymore. But usually when we talk about the lifetime we refer is not the lifetime of individual item, it's a lifetime of population of items. If we take a laptop as example, as a manufacturer, if the manufacturer produce 1 million laptops, what they care about is the lifetime of this 1 million laptop. So in this way, it is actually a percentile lifetime. This lifetime is defined at a certain percentage of reliability. Let's say if we define the lifetime at reliability level of 0.9, we call this as a B10 lifetime. This means within this time, there will be 10% failure. If 1 million laptop, that means within this time, there will be 100,000 laptop will fail. But we can also define lifetime at other reliability level, like 20% or even 1%. So this means if we want to compare the lifetime or the reliability performance of two items, we need to understand how the lifetime is defined. If we look at the mean time, like MTBF or MTTF, actually the reliability level is already very low. This means there is already more than 50% of the laptops already fail in that case. So the scientific challenge is that if we look at why items fail, here we draw, we call it load strength profile. So the strength distribution, so this x-axis is something related to the stress. Let's consider, okay, this is the temperature. And then for this item, we have inherent capability to withstand a certain temperature level. This is a rated temperature level, but because of the variation, there is, if we look at the population of the item, the capability to withstand a certain level of temperature is disputed within here. And then in the actual use, in the field operation, we have the load distribution, that the thermal stress among those population of items. The fundamental reason that they fail is there is a portion of items that the load exceeds the strength. So even though at the beginning, like for the new system, at the beginning of the design, that there is no overlap or extremely low overlap, but because of the degradation of the components, so this blue curve will shift to the left side, and then there will be becoming increasing number of failures that will come. This is because of degradation. Also, in the case of some single event failure, this means the stress experienced by the system may be exceed the design specifications or the absolute destruct limit, and then the system also failed due to the overstress due to the single event. But in order to understand, in order to do the reliability analysis or reliability design, we need to understand both the strength of the components, but also the load. Sometimes even more challenge to get a sufficient information for how the system are used and what are the operating conditions, and how to quantify the uncertainties in the load and strength, because it's all about that, to get the load and strength information in order to do the analysis. Like this is example about what we call mission profile, the long-term operation and environmental conditions. Besides normal operation conditions, sometimes there are severe users that will give some troubles for that. Okay. Another aspect of challenge is when we talk about the failure, it will come from many different reasons. Okay. If we look at system level, there are hardware, the software, the human errors. The software issue becomes more and more important, especially when we have more and more algorithms embedded in the controller or power electronic system for the control or for the auxiliary surface. So if the software fails, this may also cause the system failure. And the hardware failure, there are two types of failure. As I just mentioned, there are failure that related to the wear out. So this is a very slow process, parameter shift, and then the system, there's accumulated damage to the item and then it fails, or there is a single event related failure that catastrophically failed the system. So there are multi-source of failures that we deal with when we talk about the system level reliability. And then if we limit our focus on this like wear out, and then we see that there are a number of kind of components like active devices, passive components, and other components that we could see. So it really requires a lot of efforts to do the reliability analysis or design for the converter system. So at the research center, we focus on three aspects of research. The first aspect is related to physics of failure, try to understand the failure mechanisms, the failure mode of key power electronics components and interconnects. And the second aspect is the design verification. So talk about design for reliability, robustness, validation. So this is mainly before the products are produced. And then in the third aspect is when the products have been released to the customer side in the field operation, there's still opportunity for us to do the called intelligent control and condition monitoring, so that to ensure is reliable operation for that. In the third part of this presentation, I will quickly go through a number of research examples. Those examples are from component level to the system level, from active device to the passive components. For example, in the first example is about this multiphysics simulation. So we do simulation of this IGBT modules. This is a widely used IGBT modules for the wind power converters. It's 1.7 kilowatt, 1000 amp. So by simulation, we can emulate the periodical stress conditions. So we can simulate the deformation in the material level, so that we can estimate the lifetime for that. Besides the simulation, another method, of course, is by the testing. So here's one of the examples that we implement for the testing. For these semiconductor modules, one of the critical failure mechanisms related to the temperature variation. So the temperature variation will cause the mechanical stress at the interface between different materials in the module. So in that way, we emulate this condition by this testing setup. So this testing setup has a PWM switching. So it really emulates the operation conditions with a full voltage, and then with a PWM switching, but at accelerated testing conditions. During the testing, usually we monitor key health indicators. Like here, we monitor the voltage, the on-state voltage. So we can see that the on-state voltage is increasing along the degradation of those components. Besides the wear-out testing, we also look at the abnormal operation, like the short circuit testing for that. So this is a research activity that we use to test the short circuit capability of power semiconductors up to 10 kiloamp short circuit current. This is a long destructive testing setup, so we can do the repetitive testing, like test the short circuit for 10,000 times to see what happens on the electrical parameter level. Also, we do some research on the application-oriented degradation testing. So here's the testing for the capacitors under the humidity condition, because in the datasheet of the capacitor or application load, there's only qualification testing for the humidity for the film capacitor. Let's say you need to test under this condition for 500 hours. If you pass, and then the product is qualified. But in reality, we came across by some companies when they use a film capacitor in the feed operation, they realize that it fails very fast. And the suspected reason is the humidity. So we implement this testing. We test the capacitors under different humidity conditions and test to failure. So finally, all of the samples fails. And then in this way, we have a chance to get a model between the lifetime and the humidity. So we can see that when the humidity is relatively high, and then the predicted lifetime is relatively short. It's just 2,000 hours, for example, at 55%. But if you look at the data sheet of film capacitor that usually says it above 100,000 hours or 200,000 hours, or even more for that. So this means the humidity is a killer for the testing samples we investigated here. So this can help us to improve the system level design. Besides the wear-out testing, we also use a testing system to characterize the electrothermal characteristics of the capacitor bank in realistic cooling conditions, especially for the high power converters. If we want to optimize different assemblies, we really need better model, better electrothermal model, so that we have better we have optimized design for the whole system. Here's an example about condition monitoring. So to monitor the operation status or monitor the degradation level of components. In the upper side is an example for the IGBT modules to monitor the operation status that is on the junction temperature by observing one electrical parameters. And the bottom side is use artificial neural network method to monitor the healthy status of the capacitors based on the capacitance and ESR for that. So here's an example that we proposed what we call a two-terminal active capacitor that has a feature of tunable capacitance, because by controlling by setting the control algorithm, we can achieve tunable capacitance, but also in this concept, it retains only two terminals, so you don't need to put any extra connections or auxiliary power supplies. You just plug and play. So it has a possibility to produce like a traditional capacitor. But the advantage of this is it can replace the electrolytic capacitor by a much smaller film capacitor, or it can reduce the use of the electrolytic capacitor. We have a case study that we can save 40% of the size and keep the similar design cost. Both solutions are use electrolytic capacitors, but by adding this small PCB, we can save 40% of the space for 5.5 kilowatt single phase PV inverter application. The rest examples is about the reliability at the system level. So here is a micro PV inverter. It's a product from a company, from a startup company. So they would like to estimate the reliability of this PV inverter. Here's the procedure we do. What we call is a mission profile-based reliability analysis. Typically, we look at the long-term operation conditions, like solar radiancy and ambient temperature for a year or multiple years at these specific locations. And then we go through a number of steps, like electrical modeling, thermal modeling, and bring this lifetime modeling, and then consider the parameter variations, we can come up with the failures that related to the wear out as academic research. And then for the other kinds of failures, that some of them are experience-based. So the companies need to input the extra source of the failures, and finally we can come up with inverter level reliability analysis. Here's an example that we develop these sub-modules dedicated used for reliability aspect research for the MMC. So we develop a number of these sub-modules to form MMC converter so that we can study how the thermal stress are mutually coupled among the sub-modules, and how to optimize the location of the sub-modules and cooling system so that we can have more even distribution in the thermal stress for that. So finally, the last example I would like to show is since the reliability analysis requires a lot of modeling process, sometimes it's a challenge for the industry engineers to perform this analysis based on the long-term mission profile, based on the number of modeling steps. And that's why usually they just based on the handbooks. So that is very easy and simple, and then get the result. Okay, but the question is whether how realistic of those results based on the handbooks. So by implementing this mission profile based reliability analysis, we try to get to improve the result to be more as realistic as possible. Of course, there are still a lot of uncertainties and modeling errors and limited information on the operating conditions and so on. But still, this is more closer to the reality. So in this way, we implement a software tool that is called Design for Reliability and Robustness. In this way, we implement this software tool into 6 steps. So these are modular steps from the mission profile, environmental and operation conditions to the system. So this system, if we look a PV application example, this system includes the PV panel and the PV inverters. And then we go to the 3rd step, that is the PV inverter, and then we go down to the component level and back to the system level. So from the system to the component and back to the system level. So the users can input the data at 4 different levels, depending on what kind of information they have. If they already have the tested component level stress conditions, like the thermal, voltage, current, and so on, they can skip the rest of the first steps. So the software will run through just the last 2 steps. But if they only have the level 1 information at the system level, and then the software will go through the rest of the steps, all of the steps, to get the result. Okay, I think that's that are the examples that I would like to share. And there are still a lot of activities going on because still a lot of challenge to solve. We are continuous to work on in these areas through a number of projects. For example, now we look at also the humidity related, look at more and more humidity related failures. This project look at electronic system manufacture for climate. So how to do the climatic control, and also how to model the effect of the humidity. And then we are in the phase of developing a national level power electronics reliability testing center. So this is a 10-year project for that. That will provide us much better testing facilities compared to today. And besides the research, we also try to introduce relevant areas to our education program. As I mentioned at the beginning, that we have a number of PhD courses that is related to reliability, but also we have introduced a course called Modern Reliability from Practical Approach to the master program in your department, that including thermal engineering, electrical engineering, and mechanical engineering students. Okay, I think that's my presentation, and I would be happy to discuss during the panel discussion session. Thank you very much all for attending.
Thank you very much, Professor Wang, for your interesting presentation. We have invited also two panelists from Mexico and UK. Professor Patrick Wheeler from the University of Nottingham and Dr. José Luis Elizondo from Tecnológico de Monterrey in Mexico. I would like to give the opportunity to José Luis Elizondo if he wants to have some comments and some questions to Professor Wang, and later Professor Patrick Wheeler.
Okay, thank you very much, Marco, for this opportunity to be part of these online meetings of the Worldwide Energy Network. Congratulations to you and your team. And I have to clarify that my current affiliation with Tecnológico de Monterrey is pro bono, so I always declare it with the support of the Department of Electrical and Computer Engineering staff. My current employer is Petróleos Mexicanos. Yes, I work for the oil and gas industry, but I do research involving power electronics for renewable energy applications, especially with wind energy generation systems, where my heart and soul belong. And I would like to thank Dr. Wang for his outstanding presentation of a very relevant topic about the design of power converters, because we need to maximize the useful life of power converters, quantifying their reliability and providing all the related data along with the product to the customers. For example, data as the mean time between failure, the mean time between repair, the curves of probability of failure, thermal stress in decay, and such, are needed by the maintenance engineers in order to plan the best maintenance programs for the particular set of operational conditions of the power converters. And operational reliability, condition-based maintenance and monitoring immediately comes to our minds as maintenance engineers. When we talk about reliability of power electronics, we do not want to perform corrective maintenance anymore. We want to perform condition-based maintenance and predictive maintenance with the help of the parameters when monitoring the reliability data specific for a given power converter and its real operation condition. So I know because in 2011 I had the opportunity to be at Aalborg University, and I met a lot of great people there. And I know Vestas is working closely with Aalborg University. And Dr. Wang, I would like to ask a question. Can you give us an example of the work done with Vestas about the design reliability requirements and the qualitative and quantitative analysis methods used to verify those requirements compliance? And furthermore, is Vestas designing and building differently their power electronic devices or their wind turbines as a whole, for example, on a per wind farm basis, to maximize reliability, taking into account the specific operational conditions corresponding to very different local environments and users around the globe? And those questions arise because as maintenance engineers, we would like to be able to use reliability data specific to the location where power electronics, or in this case, wind turbines are located. Thank you very much.
Your microphone, Y1.
Yeah, thank you very much for your comments and also the questions. Regarding the first question, to give example about our collaboration with Vestas, as you comment, Aalborg University has a very long-term collaboration with Vestas to work on the wind-related activities. Specifically on this reliability related activities, we have intensive collaboration with Syster since 2011. So this is through three big projects. One is actually this Center of Reliable Power Electronics. This is a project itself from 2011 to 2016. And then later we have this APAD project, Advanced Power Electronics Technology and Tools for that. Some examples we work with them, like one of the examples I gave them for this this capacitor bank thermal characterization. So this is an example that we work together with us because they want to optimize the design, basically to design to the limit to further reduce the design cost and so on. And then we need much better model than what we have today. We need to have models that that applicable for the realistic operating conditions. So that for this capacitor bank, we need to implement a realistic cooling conditions, so that we can see what are the actual thermal impedance, thermal resistance for the capacitors. This is one example. And another example is there were activities that we do the cycling testing of active power converters and so on. Of course, there's also some other activities together with Vestas. But as far as I see from the wind industry, they put more and more efforts on the surface. So in the past, they sell the system, okay, the wind turbine to do the installation. Now they also at the package. They say they can sell 25 years of surface to wind farm. So every year they can maintain a certain amount of electricity generation. If they cannot fulfill this target, and then they will pay to their customer for a certain penalty. But then if they can achieve that, of course, they get profit from the surface. So this becomes more and more the key, the core competence for the industry. Because nowadays, many companies can somehow produce, can provide the wind turbines or the wind farm solutions. But if we look at the long-term performance, this will be the key. This will be the key. How we can maintain a long-term reliable operation and maximize the energy generation. So in order to do this, the industry needs not only just, let's say in the past, like we qualify the products according to certain standard and then we sell to the market, but it's really about to understand the system they designed, so that they can have optimized maintenance program to ensure the energy generation, and also meanwhile to reduce the efforts to do the maintenance, so that they can get profit from this part. This is what we see with the wind industry. And I think your second question is related to we need to design the converters that specific to the operation and environmental conditions to optimize that. Is that on that? Maybe yeah. Can you repeat your question on that aspect?
Yes, of course. We know that the reliability of talking about any equipment, not just power electronics,
yeah,
is related to the very specific local environment and even the kind of users like you presented, right?
Yeah.
And if we design an equipment with a specific standard, and like you said, we sell it to the market, we will find that it will not operate the same in the desert and in the jungle, for example. The humidity levels, the temperature, the thermal cycle, the temperature cycling will be very different. So is Vestas in this case, or any other company, trying to design their products specifically to some locations, or they will be designing it the same from now on? I mean, this trend of applying reliability engineering to power electronics is really ongoing, and I would like to know from you, from the people who is working closely with the wind energy companies, what are they doing, or what are they thinking about that?
I think this is definitely a very good point, and also opportunity to optimize, to customize the system. But the scenarios are quite different. For example, as far as we know, at the moment, the hardware system is still the same. But of course, when they design hardware system, it's a modular design. It's very easy to scale it up or scale it down. But for different locations, the hardware system, the structure is almost fixed, because this takes a lot of efforts and time to fix a certain design platform. But then for different locations, we can use software algorithm to optimize. So the software can be more easily to change, to update, and then to dedicate it to those areas for the operation. So usually we can manipulate the software for the same hardware system. So this is some companies say they implement this to do the optimization.
Thank you very much, Dr. Wang. Marco?
You're welcome.
Thank you very much for the discussion. Now I would like to offer to Professor Wheeler to provide some comments and some questions, if there are any. Professor Wheeler.
Hi, good afternoon, everyone, or good morning. First of all, a big thank you to Marco for inviting me, and to Dr. Wang for the very interesting presentation. There's a lot of very good material and a lot of work in there. Reliability is always something that's interesting and means different things to different people in different application areas.
Yeah.
I always quote the difference between aerospace and automotive. They're both interested in the concept of reliability, because they would both like to take benefit of that. Aerospace to reduce maintenance, and automotive to understand the reliability so that they can make components that don't cost too much. So in aerospace, you're often looking to understand how long the component will last, or and how you can make it longer, or how you can predict its failure. In automotive, they want something that's going to last exactly 10 years and then fail at the end of the lifetime of the car, and they don't want to pay for it to last any longer than that. So different motivations, and the talk we heard today was in the energy sector. So again, the motivations are always different. One thing we also ought to take care about is not just reliability, but is availability. One of the things we can do in power electronics is to build redundancy into a system. When you do that, the reliability goes down because you have a bigger system, more complicated system. But the ability of the system to provide energy or to process energy will remain even if there's failures. So that's something that I believe is considered, and it has historically been used in the electrical energy sector. The idea of building in redundancy into the design, not to improve reliability, but to improve availability, i.e. the system will continue to function even though there's been a catastrophic failure in part of that system. And that's an important concept if, as you were just discussing, you're paid by the hour that you deliver renewable energy to the grid. It's very important that the system might continue to operate even though there's been failures. And that same technique is used on an aeroplane. There's always 3 actuators for each surface on an aircraft. If one actuator fails, you as a passenger know nothing about it. The aircraft continues to fly perfectly well with just 2 actuators on that surface. But it will get to its destination. It meets its requirement, and then you can change things when you need to. My second comment is really around how to calculate reliability and what that means. One of the concepts I like personally is the idea of lifetime consumption modeling based on the actual use and environment of the converter. So getting away from the idea of replacing a piece of equipment after 5 years and moving to that equipment monitoring itself, maybe using condition monitoring or maybe using environmental and usage monitoring, so that it knows when parts of the converter are going to fail. The only way you can do that is with a physics of failure model. And Dr. Wang, I wondered if you wanted to comment a little bit more about the approach you take in actually looking at reliability from the idea of why things fail and how you model why things fail, and therefore how that feeds into either the way you design things or into that concept of understanding the failure of the equipment based on how internally within some component, maybe a power device package, maybe a microprocessor package, how that device is going to fail. So yeah, my 2 comments or questions, one is around the difference between reliability and availability, and the other is around that physics of failure model and how that feeds into some sort of lifetime consumption modeling. Over to you, Dr. Wang.
Thank you very much. Wang, your microphone.
Yeah, thank you, Professor Wiener, for your comments and questions. And definitely they're very good comments. So the first comments is about the availability and the reliability. Yes, I fully agree that the availability is for some application is very important, and also it's reliability related. For example, the availability, if we introduce redundant system, and then of course, because the system becomes more complicated, and then the reliability itself maybe could be reduced. But then because of the redundancy, and we can maintain a high reliable operation within a short period of time, so that we can make sure that the system is already on, is already ready for the work. This is very relevant, of course. And then the second question is related to how we take into account or how we utilize this physics of failure-based models in this lifetime prediction or reliability analysis for the power electronics converters. Is the physics of failure model. There are 2 different types of models that, or we say two different tracks on the reliability engineering that people go. One is more based on the physics of failure, so based on the understanding at the material level, at the process, to see how components or the interconnects between components they fail. Another track is based on the accelerated testing, the fit experience, so based on statistics, and then to come up these models to do the prediction. But these 2 actually can be, there are a lot of correlation between these 2 tracks. For example, if we look at some of the existing physics of failure-based models, those models, the parameters are related to some of the material parameters and so on. Some of them it's very itself, of course, it can still be able to implement in the reliability prediction process, like what we gave the example is this micro PV inverter, there are models. So you can either choose empirical based models or choose physics of failure based models to do the analysis. But also another correlation actually is what we prefer after a lot of discussions and try to implement different models, we could see that actually those empirical-based models, they're very easy to use compared to physics of failure-based models. Talking about the model itself, but then we would use like the physics of failure-based understanding. So how to choose the right empirical model and how to interpret the limitations of the models itself. And then if we look at a model that describes the dependency between the lifetime and temperature and voltage and humidity. And what we need to understand is that for a given failure mechanism, whether this model is relevant or in the real operation, if there are multiple failure mechanisms in principle, but then based on the pattern of the operating conditions and which kind of failure mechanisms will become the dominant. And then we will choose the right model that describes this dominant failure mechanism, because theoretically there are different failure mechanisms, but if the mission profile is a specific one, and then maybe some of the failure mechanism is not relevant anymore, or is not dominant anymore at least. And then based on the physics of failure understanding, we can understand better for a given application, what would be the dominant failure mechanisms, and then we can still choose empirical based models, but we choose the right one. This is one thing. Another thing is based on the physics of failure understanding, we can have better understanding about the applicability of those models. If you look at model describe temperature voltage, usually it does not specify what is the range of the voltage, what is the range of the temperature that this model is applicable. If we don't just take capacitor as an example, for example, if there is a model provided by manufacturers, but then there is a voltage derating factor. It's the inverse power law usually, but the voltage, this model is actually is applicable for a quite limited range of voltage around the rated value. If the voltage stress is way below the rated one, this model is no longer applicable, and then the effect of the voltage will become insignificant. So all of these information can be this physics of failure aspect research can help us to understand those things. And no matter we use finally the empirical based models or physics of failure based models, these are very helpful for that. I hope this reply to that. Thank you very much.
Thank you, Dr. Wang. I'm Mariel Villalon. I'm introduced to you. I think Jose Luis and Patrick, they already know me, but I will do the question from the audience to you all. You know, it was very interesting, the comment from Jose Luis about asking about the reliability in the wind energy sector. I would like you to have some comments on the solar power sector, maybe, because in general it's thought, but I think it's not correct, but you can tell me about that the guarantees, in commercial guarantees, are not very well developed in solar, but in the case of wind, they are very, it is well known that they're very, I don't know, very strong in a way. You know, I would like you to have some comments on that, and how is that related to the reliability assessment to solar photovoltaics, especially.
Yes, thank you, Professor Filon, and your question regarding the solar application. Some of the motivations are quite also relevant to those we discussed for the wind application. But if we look at a solar application, especially a PV application, look at a PV plant. Nowadays, these PV panels is a dominant part in terms of the initial cost. And the warranty time of a PV panel can go like 20, 30 years. So it's relatively reliable for the whole life of the PV plant. And if we look at PV inverters, depending on the design, some microinverters, they try to design the microinverter to match the lifetime of the PV panels. But for the central type or screen type, and this at moment, at least from the warranty period point of view, it still cannot match what we have nowadays for the PV panel. So this means probably along the surface life of the whole PV plant, we may need to replace the PV inverters. This is one concept, like replace the PV inverters. Another concept is that we try to design that, because the limitation, the challenge does not necessarily come from the technology point of view. It's all about the design. If you can design wind power converters for 25 years of operation, we can also design a PV inverter for that. It's all about the calculation about the overall life cycle cost for that. Yeah.
Thank you very much, Dr. Wang. I would like Patrick. There is a question for Patrick. Pat, in a power electronics based power system that we have so far, maybe more in the near future. Dr. Wang, can you? I think we have some kind of echo from one of your devices. I think we'll. Can you? Okay. In a power we have so far in the near, how this reliability applied to these power electronic devices will affect or not the reliability of the whole power system. And for example, if you can give some comments as well for example for a smaller power system, maybe a microgrid or something. But we would like to have some comments on that. What can you say about that, Pat?
So if I've understood you correctly, you're talking about the reliability of power electronic components on the security of supply of electrical energy, say in a microgrid, yes?
Yeah, as a big power system, and then some comments on microgrids.
Yeah. Okay. So I mean, this goes back to my comment. If you have power electronic components such as device packaging that have a particular reliability, but you want a system to have maintenance at particular intervals, then you may be in a position where you have to accept failures. And the work we've heard today is great, because that's exactly what you want to understand to be able to predict when those failures are going to occur. Now, then you've got two choices. One is to improve the lifetime, but that can get quite expensive. It's not technically impossible to do, but it could affect performance and can affect cost. Or you accept that you're going to have those failures and you build in the redundancy. Now, in a large power system for a country, that's quite easy, because you have many generation stations, many different sources of electrical energy connected to that grid. And if you lose one of them, then the network should stay stable. Doesn't always, but it should do if it's operated correctly. I have to say there has been a situation in the UK in the last year where that wasn't quite the case, but it should be. So if you get your design of your electrical system right on a large scale, then one generation source failing doesn't matter. If you go down to a microgrid, then you're more susceptible. You could still think about a microgrid where there's many sources, and so certain sources will act as backups for others. We were talking about PV, solar energy just now, and it's quite common to also think about energy storage when you're thinking about a PV generation source. And of course, in that situation, if there was a small failure in your power converter, then for a short time, you can obviously feed that grid from that energy storage. So to me, this understanding of reliability is vital and very, very important, because it allows you to design the system to meet those security of supply requirements that you might have in an energy system. And if you think about it in that way, I believe that you should then end up with an electrical supply. Doesn't matter if it's a microgrid or on a transportation system or for a whole country, that should be able to provide you electrical energy with the reliability of that source of supply that you define. And it becomes then a choice of cost about how reliable you make that source of supply. If that answers your question, I hope.
Oh, so. Yeah. Thank you, Pat. Thank you. I would like to ask to Jose Luis. You mentioned something about the maintenance. Okay, I think this is maybe. I think reliability is related to predictive maintenance. We should get at some point to there. That's the thing. If that relationship is right, is exists or not, how is that relationship, and how is used in the industry, according as you know, regarding especially in these power converters, for example. Jose Luis?
Yes, thank you very much for your question, and I can give you some comments about reliability in maintenance, because with my experience in the oil and gas industry, reliability and operational conditions are seen every day. We don't want to perform any more. We don't want any corrective maintenance going on. We want to know when an equipment is going to fail, and we want to know exactly the moment when we are able to make the maintenance, because maybe there will be some situations where we cannot stop the process, but we must be prepared to do the necessary maintenance if that maintenance is required. And the maintenance based on the operational conditions needs to have monitoring devices installed. We need data. We need not just the data from the manufacturer, from the companies which manufacture the equipment. And I'm not talking about just power converters. I'm talking about any kind of equipment. We want data from the local environment and with the local kind of usage of that equipment. We are very familiar with the data sheets where they inform some sort of curve, but it is very specific for example, a 25 degrees Celsius of temperature. And it is a constant test done in the industry before the product goes out. But we need the information for a variety of temperatures, for a range of temperatures, for thermal cycling, to know the decay or the degradation of the product. So this is a rather difficult thing to do when we don't have the necessary models to accurately predict the lifetime of a determined equipment. But as an ongoing trend, we are seeing some pathways which we can go through to achieve this, and not just in power converters, but in any kind of equipment.
Thank you, Jose Luis. Actually, we have a comment from Mauricio Chamorro saying that we need complete and constant information on many variables, and for that we must strengthen the data infrastructure, that we have available, in this energy installation and so on. So thank you, Mauricio, for your comment. And thank you, Jose Luis. We have a question from Jose Riveros. I have to tell you, Dr. Wang, Pat, and Jose Luis, and all of you that we have a lot of friends from Paraguay, Argentina, very parts of our countries. We have some friends from India as well. And there is a question from Jose Riveros. And I think that question should go to Dr. Wang. Do you know, and this is a very good question, do you know if the control strategy is also included in the analysis of the reliability? Is it any control technique more likely to produce failures in power converters?
Yeah, the control. I think there, in the top level, the control algorithm itself is the software part. So, as I mentioned, the software is also a source of the failure. Definitely, this control strategy itself could be a source of failure from the software part itself. In our research, we didn't focus on we haven't focused on the software part, but even for the hardware part, definitely different control strategies will introduce different stress level, different power loss on the component level. So this will affect the predicted reliability. So this part has been taken into account when we do the power loss model, thermal model, and then this it is control specific analysis.
Okay. Patrick, can you give us some light on this as well? Okay, I think
I don't think I've got anything to add to that one. I tend to agree with what Dr. Wang's just been saying. That's a good answer.
Okay, thank you. Of course, a failure in software may cause a total failure of a system, talking about this. For example, how is this issue applied for high technology-based applications for power electronics? For instance, you mentioned something about aircraft, maybe for mobility applications, electric vehicles, Dr. Wang, or maybe Pat, I don't know, if you wish. Pat, can you give us some?
If maybe I could say something about that one. So, but maybe a little bit more generally as well. So, I'm not sure reliability is the right word to use in relationship to software. It's more about the integrity of the code, and if something does go wrong, what's the consequence of that? And there's various standards and various protocols for dealing with that. So when you're looking at software integrity, I think that's probably the better way to think about that. Software shouldn't fail in an unpredictable way. Software should be determined, or can be written to be deterministic. And if it's deterministic, then that software will have certain consequences for certain inputs. And that's where the issue comes, is it's not necessarily the software that will have an issue. It's the software being confused by what it's being told. And one of the things you need to be careful of is introducing too many sensors and too many additional points of failure to the system. When you're doing condition monitoring, for example, can you use the signals you're using for the control, or do you really need additional sensors? And if you're putting in those additional sensors, are you adding to reliability problems? It's notable that when you're on an aircraft and there's an issue with an engine, it's most likely to be a sensor failure, telling you that there's something wrong with the engine, but it's not something wrong with the engine, it's something wrong with the sensor. And you've got to be very careful that you don't design a system where actually it's the monitoring systems and the measurement systems linked to the software that are going to cause you more failures than the actual physical system itself. So I'm not sure if that answered your question, but it's certainly related.
Thank you, Pat. Another question from Santiago Verne. How do you verify your reliability models and simulation with real experimental results, given that real lifetime of power converters are expected to be in the range of several years? Wang? Dr. Wang? Yes.
Yeah. Usually, what the verification could come from different levels. So at the component level, what we verify is like we can verify the different stress level, like your thermal stress, your humidity level, and also the models, the lifetime models of the components could come from the accelerated testing, and those models come from the accelerated testing, and those stress models are validated. And then if we want to validate at the converter level, let's say a converter, and then you want to validate the predicted converter level lifetime. This is really challenging part. This is really challenging part. But one way to do that is there is a kind of testing called one life test. So basically, you can verify that the lifetime of this converter is less than a certain years. But it's difficult for us to validate like the exact years, unless you let the converter run in the field for 20 years. But then the motivation to do this is not justified, because if you wait for 20 years to validate your model, and then in 20 years everything is changed, technology is changed, components changed. But it's more about that we can validate from step to step. Each of the steps we try to reduce the uncertainties. It's more about, so if you look at the modeling process, there are different models, steps, different data input. So what we can do is we try to reduce the uncertainties in each of the steps, reduce the errors of each of the steps. And then collectively, this will lead us a more realistic prediction. But the target is not to have a 100% accuracy. It's not 100% accuracy, because the reliability prediction is like you predict the life of a person. There's so many uncertainties in the factors, but based on this prediction, especially like the lifetime prediction, the wear out prediction, we can avoid the scenario when there is some improper design. Let's say if we select the components for converter design, if we do this kind of lifetime prediction, we have better chance to avoid that in a scenario that in the field operation there was a high percentage of failure come from the wear out failure. A proper design will exclude, only allow a very limited number of failures that comes from wear out, because otherwise there is a high percentage of failure within the surface life. So that's why regarding the validation, we do validation at a different level, at the stress level, at the lifetime model part, and also we implement converter level testing to validate that the lifetime of this converter, of course, at accelerated condition, statistically we can predict, okay, its lifetime is shorter than a certain amount of years. This is the way that we do validation.
Thank you very much, Dr. Wang. We have another question from Mariana Rojas, and I will introduce this more or less. Especially, you know, the regulators of the electrical system, they have to in some way make these devices to accomplish to the grid codes. Okay, so I can say maybe Jose Luis or Dr. Wang, but Jose Luis first, please. How can electric regulation, thinking of that, you know, about these devices, power converters, how can electric regulation yes, can electric regulation help on the process of making decrease the energy loss production in order to accomplish with the grid codes, you know, more or less? What can you say about that, Jose Luis? Maybe here in Chile, we have always the regulators trying to put a lot of requirement, for example, for power converters in order to be connected to the grid. You know, what happens in Mexico? What can you say about that, or the rest of the world?
Well, in the case of Mexico, like with the petroleum industry, it is a state industry. So with the electricity, there's also a state company ruling all of that. And we have a commission to regulate energy. So I can say that regulation, more than helping, it adapts to new technologies. And with the current transmissions lines in Mexico, there are a lot of areas of opportunity to work with. So maybe the regulation will get adapted too before it really helps to achieve more reliability.
Dr. Wang, can you say something on that? Can you add something? Would you like, or Pat maybe?
Yeah, I think the regulation, definitely, as you mentioned, there are different grid codes on that, and also different regulations or emerging requirement will affect the design of the power converter itself. This grid profile, the grid profile itself is also part of a mission profile, the operating conditions of the converter. So this also affects when we do the reliability analysis and so on.
Yeah. There's a question about that about the standard codes of this. I'm looking for it. It's related to the. Well, do you think maybe to Dr. Wang or Pat? Do you think IAC standard for reliability of electronic parts are useful? They don't consider mission profile. There's a comment from Mohsen Raimian. A 1217 handbook.
Yeah, there are always reasons that they exist because it depends. It always depends on the information you have or at which phase you use the reliability prediction. For example, if you have the very initial phase of your product design at the very concept phase, the purpose is just to benchmark some technologies. So you use a handbook or this IEC standard method, you can very quickly to benchmark different technologies, so you can choose the preferable one. So from this purpose, it's still okay, even though those methods, they didn't consider many things, like the actual operating conditions, how your control strategy will affect that. It is very rough estimation. But for this purpose, it's okay, just from my perspective. And then after you have more details of your design, you have fixed topology control, you have selected components, and then if you want to have more realistic estimation, and then you can apply a more the method that based on the mission profile or based on the models that directly came from the accelerated testing of the component you use. So, and then you improve the prediction accuracy along the design phase and based on the available information for that.
Thank you, Dr. Wang. I would like to ask you for comments, final comment. Dr. Patrick, please. Can you give us your final comments on this?
Yeah, no, it's been an interesting session. So you're talking about the session overall, not just the question, yes?
Yeah, I think we're running out of time, you know. So
yeah, that's okay. So no, it's been a very interesting session with a lot of very good questions and a lot of very good points raised. And yeah, Dr. Wang did a very good job of introducing the subject. It's an important subject. It's something which you have to think of in context of your application. But I think we've had a very interesting session, and it's raised a lot of the pertinent points around this area, and I think there's been plenty there to think about, which is good.
Thank you, Dr. Pat. Jose Luis?
Yes, well, take the opportunity to thank you all again, Ariel, Cristina, Marco, all the University of Talca staff for organizing these online meetings. Thank you very much, Dr. Wang from the Aalborg University for sharing his knowledge and his experience with the industry and the academic world. And well, let's keep up the good work and keep contributing to the benefit of humanity, like the IEEE motto says. Thank you.
Thank you, Jose Luis. Dr. Wang, your final comments? Your microphone is shut. No, you're right.
For joining this seminar and also these inspiring discussions. Reliability is a topic that still have a lot of challenges, and I'm very happy to discuss with everyone and also receive a lot of feedbacks. And thank you very much.
Thank you very much, Dr. Wang. Cristina, Marco? Cristina?
Yeah. Yes, I would like to thank all the speakers, panelists, and also the public that has been attending us today. I think it's been a very interesting conversation, and so I want to thank you again for your assistance and for your participation. I would like to invite you to our next session, who will be held on the 25th August. It will be in Spanish, because you know we alternate English and Spanish. Yeah. So I'm going to share the banner so you can check. It will be Smart Grid, una oportunidad de optimización. And it would be in charge of Luis Garcia, Grace Quintana, Pedro Bañuelos, y Noelia Uribe. So I'm pretty sure it would be also very interesting, and also in the line that we have been talking these latest sessions. My final call, it would be for all of you, for all the public, to tell you that if you would like to participate with us as a panelist or as a speaker, as a main speaker, if you have a theme and you want to just participate on the conversation, so just write us. You have my email on, well, you have the chat here in Zoom or YouTube, but also you have my email, because I have sent you all the invitations to this Zoom session. So please write us and just propose a theme so we can arrange a date for you. Okay. So thank you very much all for your attendance today.
Thank you very much. Thank you all. Bye-bye.
Okay, thank you very much. We are finishing this session. So, thank you, Professor Juan, Professor Wheeler, and Jose Luis for all your support today. And we hope to see you soon again. Goodbye to everyone.
Bye-bye.
Bye-bye. Thank you.
Bye.
Thank you all.